Good morning, Chem 1. Today's the last day of real content in this class. After this, we'll have a kind of a short little Unit 13 assessment and you will be done. There are two extra credit opportunities this quarter. One of them will be today, and it'll be in the video. I'll show you what you can do and it'll make more sense once we talk about today's topic. And then one will be next week. We'll have a Zoom meeting and just to kind of have a final class goodbye, and then you'll be able to, if you show up to that, you'll get a little extra credit. Okay? Remember, you can retake any quizzes that you've taken up to this point, and we're still accepting work here for the next couple weeks, so you still got time. We're just letting you know how the year is going to end. So let's go ahead and get started, and we'll get to that extra credit, which it's good. It'll be fun if you do it. Today we're going to talk about colligative properties. We've been talking about solutions. A colligative property is a physical property of a solution that changes because the solute is present. All right. If you look at this graphic down here, we have a pure solvent. So you could think of this as water. And then here we have a solvent plus a solute. Well, when you have a solute dissolved in a solvent, it does things like change boiling point and freezing point and vapor pressure and osmotic pressure. Today, we are only going to talk about boiling and freezing point and how those change when you add a solute. And you might be thinking to yourself, well, I know some of this a little bit, because we put salt on the roads, for instance, to lower the freezing point of water so that there is no snow on the roads at 32 degrees, because the salt drops the freezing point. We call this freezing point depression to below 32. And we'll talk a little bit about this as we go through the math. There's a little math, it's not too bad. In order to do these equations, in order to understand these colligative properties, we need to understand the difference between strong electrolytes, weak electrolytes, and non-electrolyte. An electrolyte is something that when it's dissolved, it can conduct electricity and typically has ions involved. The strong electrolytes are typically ionic compounds, all ionic compounds, strong acids and strong bases. So here's your list of strong acids and strong bases. And then ionic compounds would be any cation, which is typically a metal, or anion, which is typically a nonmetal, but it could be polyatomics as well. So anytime you see those things, you should know that they're going to completely disassociate in water, and that matters. We'll get to why here in a little bit. Weak electrolytes would be something that you put in water and they kind of partially dissolve, or they might partially disassociate, but not completely. Typically, when we're talking about acids, we talk about weak acids and weak bases. Ammonia, acetic acid, this is hydrofluoric acid. Those type of things would be weak acids and weak bases and would not completely disassociate in water. That would affect the math. We're not going to deal a lot with these in the math, but just know they mostly stay together and therefore would behave somewhere in between a molecular and ionic compound. All right, but we're probably going to deal with these a whole lot from a math perspective. And then finally, we have non-electrolytes. Non-electrolytes they will dissolve, but they won't disassociate. So typically, these things are covalently bonded. When you have an alcohol like methanol, ethanol, or this would be methanol, okay? I guess that's a repeat of the first thing. Or like if you have a sugar, anything that ends in ose, like glucose or sucrose, those things don't disassociate into a cation and anion. And therefore, they stay together as a molecule and they will only create one particle within a solution. All right, so how is that different than the ionic? So now we got strong, weak, and non-electrolytes. Let's try to explain what we're talking about here. The reason this matters is because within the math, we need to know, okay, if we're going to start talking about boiling point elevation, and we talk about, let's say we're going to make water molecules circles. All right, and if I put salt in that water, and we'll make those squares, the amount of salt, or the amount of particles in the water, is going to elevate the boiling point more or less. So the more salt you add, the higher the boiling point is elevated. And so the more particles that are in the solution will affect how much the boiling point is elevated and the freezing point is depressed. Which means we need to know how these things are dissolving or disassociating so we can count particles. For instance, HBr is a strong acid, and it will disassociate into H plus and Br minus. That is 2 particles. That 2 is going to become important here when we start doing the math. All right? C2H5OH is ethanol. It's covalently bonded, and therefore it's not going to disassociate into parts, and therefore it's only going to make 1 particle. CO3 is a polyatomic ion that's going to stay together and be 1 particle. And that means we have 2 H plus particles, because there's 2 of them. It shows us right here in the formula. So that means this would have a total of 3 particles within H2CO3. Same thing down here. We have 1 Mg, and we have a Br minus 1 and another Br minus 1. That's 3 particles. That 3 is going to be important. CaOH. You got a Ca, you got OH, and you got another OH. Okay? 3 particles. Sucrose, if it ends in ose or all, those are covalent, which means they'll only make 1. It's not going to disassociate. Okay? So what does this all mean? Well, when we start to look at the equation for how to figure out how much the boiling point or freezing point moves, there is a number in that equation that's I. That I is the amount of particles. All right, so you got to remember that, because it's going to change your answer quite a bit. We will only do this for water as a solvent, and therefore you are only going to use the Kb factor, the constant, for water. So this is for boiling point elevation. What this equation can tell us is, based on the molality of the solution, how much the boiling point will elevate for water. All right, so in other words, if I have water and I'm pure water and it boils, we know it'll boil at 100 degrees Celsius. What this equation does is it shows us, if I add salt, depending on how much I add, how much will the boiling point elevate. So Kb is a constant that you will always know. M is the molality, and I is the number of particles. And that will give us the change in temperature of the boiling point. Here's the thing. That's only telling you how much the boiling point is changing. It's not telling you the new boiling point. To get to the new boiling point, you would need to add it to 100 degrees, because that is the boiling point. All right, let me show you what these look like, and I think maybe it'll make a little more sense. It says, what is the boiling point for a 2.5 molal solution of methyl alcohol? Methyl alcohol is covalently bonded. That means 1 particle. That would be the first thing that I would identify. How many particles are we dealing with here? So then when we do this equation, we take Kb for water, which is 0.52. We take the molality, which is lowercase m, and we take the number of particles, which in this case was 1. We do the math out and we get 1.3. What this means is the boiling point will elevate, it's called boiling point elevation, will elevate 1.3 degrees. So now we just need to tack that onto the 100 degrees that we know the boiling point of water typically is, and that gives us 101.3. That's the new boiling point based on this solution. All right, let's look at another one. What's the boiling point for a 2.5 molal solution of sodium chloride? So the molality here is the same. The difference here is sodium chloride is not covalently bonded. It's a cation and an anion that will disassociate into 2 different particles. So now the Kb for water is still 0.52. The molal solution is still 2.5, but now we have 2 particles. We do that out, and guess what? The colligative property for boiling point changes, it doubles to 2.6, meaning the new boiling point is 102.6 degrees Celsius. That's all it is. The KB will be given to you, the molality will be given to you. Your job is to just simply come up with how many particles this substance has. All right, here's another one. So not only can we raise the boiling point of a liquid by putting solute in, we can also lower the freezing point. And this is when it becomes helpful to us when we're talking about, winter in Ohio, we put salt on the roads because we're trying to lower the boiling point, our freezing point, so that the water is still liquid and not dangerous on the roads. We don't want ice. Same idea. Now the constant is different. Its Kf is 1.6. And we still need a molal solution, and we still need I, the number of particles. In this case, though, oh, there's a mistake on this slide. In the water is 0 degrees Celsius. I can't believe that's there. Okay. Once we subtract, or once we find how much the freezing point will be depressed, we need to subtract it from 0, meaning that freezing point depression will always be a negative number. Let me show you what I mean. What is the freezing point of a 3.0 solution of methyl alcohol? Well, we know methyl alcohol is covalently bonded, so that's only one particle. Okay. The Kf is 1.6 always. The molal solution is 3, and we know methyl alcohol is a 1 particle. And so if we do the math, we get 5.6 degrees. We need to subtract that from 0, though, so that the new freezing point is negative 5.6. All right? So with boiling point, we add the difference in temperature to 100. And with freezing point, we subtract the difference in temperature from 0. Because boiling point elevates and freezing point goes down, depresses. Another example, now we're talking calcium chloride. You need to know the formula here. Calcium chloride is CaCl2. That will dissociate into 1 calcium, 2 chlorines, which is 3 particles. The Kf is 1.86, the molal solution is 3, and the number of particles is 3. That means this will change by a factor of 17. We subtract that from 0, and we get negative 17 degrees Celsius. The most difficult part of this is just knowing how many particles that solute is going to dissociate into, if any at all. It might just be 1 if it's covalently bonded. But that's pretty much, that's everything. So you're thinking to yourself, all right, I sat through all this. Where's the extra credit, Mr. Hess? Well, every year in chemistry, around this time, you may have seen us doing this before. We make ice cream out in the front yard, out in the front open. Foyer area. And since we're not in school, we're not able to do that. So I made a short video that's going to show you how to make your own homemade ice cream in a couple Ziploc bags at home with some help from my kids. The instructions are in the video. It's pretty straightforward and simple. We did it on Saturday. It was really easy. You need a couple things. If you have, and it's not too bad. If you do this, if you make your own homemade ice cream, and you don't even have to use a Ziploc. If you have a homemade ice cream maker and do this, I'll accept that. And take pictures of yourself making the ice cream or showing me the ice cream you made in your Ziploc bag. I will give you extra credit. You would simply just have to send me the picture of you making ice cream through school mail. All right? So why does this have to do with what we're talking about, Mr. Hess? Well, when you make homemade ice cream, you put a lot of salt in the ice. Why do you do that? Because you're trying to lower the freezing point and cool that milk sugar solution down as much as possible. Okay? So not only is salt on the solute salt good to keep it safe on the roads, it also tastes good if you use it correctly. So check out the video. Once again, totally optional. Make your ice cream, send me a picture, I'll throw some extra credit your way, all right? Good stuff. Pay attention for next week. There will be a Zoom meeting with some extra credit tied to it potentially. Have a good weekend. We will see you next week, hopefully. Bye.